Hello, this is the sixth video in a little mini series that I'm calling Basic Limit Theorems, and today we're going to look at the central limit theorem. And the theorem says that if we have a random variable x, I, that are IID, random variables with mean, mu, and variance sigma squared, both finite, and we let capital G of n equal this probability, which is like a distribution function. It's this random variable less than or equal to x, and phi equal the distribution function for a standard normal distribution. Then G of n converges in distribution to phi of x, and it's uniformly in for all x in the real number line. So let's just start in on the proof. Let's let little g be the characteristic function of capital G, and phi be the characteristic function of phi. Then phi, the characteristic function is of standard normal is this, and that's for all t. Then by Levy's continuity theorem, we need to show that the characteristic function converges to this characteristic function that we know. And this is for t in real number line, which will imply that the distribution functions converge, and that's really what we're after here. And then by Polya's theorem, we know that the convergence is uniform. Okay, so one note that here, remember, capital G is this less than or equal to some x. So let's look at study that piece a little bit, which is this. So if we divide everything by square root of n, then we can make this look like this, and then or divide by n everywhere, and then we can take this and the top make it into a sum, which is this. And then the bottom, of course, stays the same. But if we look at this piece right here and we call it xi, we've just standardized it. So the xj's are independent, or they're IID random variables because of the xj's were IID random variables. And the mean of z, which is mean of this, is 0, and the variance of this is 1, which is, the variance of z. And so this is going to play a part, because when we look at the moment generating function of z, take the first derivative, set it equal to t equal to 0, you get the mean of it, which is 0, and take the second derivative, set it to 0, it's the second moment, which is 1. So we're going to be using that in this next page. So now if we look at the moment generating function, little g, and that's of this random variable here. Now, and I have a video on characteristic functions that say when you multiply or divide by a constant, you can really take it into the function or the argument section like this. And then we're left with the sum of IID random variables. They're all independent. So then there's a property that says really you just need to look at one of them and raise it to the nth power. So that's what we do. So this is the moment generating function. We want to show that it converges to a known characteristic function. And so now let's look at this for a second. So if you evaluate it at 0, it's 1, because it's the expected value of ITX divided by n. If you let it go to t equal 1 at 0, it's 1. Take the first derivative, then properties of characteristic functions, we get I times the mean, which we said was 0, and take the second derivative, we get I squared times the second moment, which, since this is -1 and this is 1, the answer is -1. So now let's consider a Taylor expansion of the moment generating function around 0, which often people call a Maclaurin series. So that's this function here. So it's our original moment generating function, and then we evaluate it at 0, and then we take the first derivative times you have to use the chain rule, so that constant comes out, and then it's the second derivative and then there's a chain rule associated with it. Oh, this is, you know, times the, I guess it'd be x minus a squared piece, and then divided by the square root of 2, and then the remainder is of small order. That's called little o notation. I have a video called, you know, big O, little o notation, and it explains that this really goes away at a rate of t squared over n. So it goes, the bigger and bigger an n gets, the smaller and smaller this n, and it really goes to 0. So in asymptotically, we can ignore it. So now here we have 1. This piece, because it's g, it's 0, so that goes away. And this was minus 1, so we put in minus 1 t squared over, you know, divided by 2n, and then we get this little o notation here. This little o notation can be rewritten into t squared times, you know, t squared over n times little o of 1. It says this goes to 0 at an order of, you know, 1 over n, just goes away. So I like it like this because we can factor out, say, a t squared over n on this term here, and that's what we do. Now there would make it a constant in front of this, but it's still, you can put that into this term and it's still a little o of 1. Well, as this goes to well, okay, so that's the one, that's our moment generating function. Now if we put it back into our original moment generating function, which is raised to the nth power up here, then this kind of looks like the e function, right? So if we let this go to the infinity, g of t, you know, this, you know, the 2 can be thought of as the squared, and this goes up there too, but this goes from 1, and this is 0, so it's just 1, and we're left with t squared over 2. And this is the characteristic function for a standard normal random variable. So the characteristic function converges, which says that the distributions converge, which then proves the theorem. One note is we often write it as that this is approximately standard normal, or sometimes we write it like this, where this is a sum, and then the mean of the sum, the standard deviation of that sum, is approximately normal. So let's look at an application here. Let's let xj be IID, and they have some mean and some variance. So we're not telling you about what the underlying distribution is. We just know that the mean and variance are finite. So then, according to the central limit theorem, then we can use the standard normal distribution to approximate this probability. And this is how you do it. So notice that there's no equal sign there, and I'll show you in a second. In a continuous setting, that doesn't really matter, but if it's a discrete case, then it does matter. So then if we subtract the mean of that and divide by the standard deviation everywhere, we get this. But this right here we showed went to standard normal. So we can look at the probability oh yeah, because we said this is the mean, and there's n of them, so we got n mu, and then this, they're n of IID, so it's the variance would be n times sigma squared, so the standard deviation is sigma squared of n. So I just plugged in the values here. And then this is the standard normal distribution, which says we can take the probability of being less than that minus the probability of being less than that. And so this is where that equal to sign comes in. So we get rid of the a here because we're strictly greater up here. And so we have to be careful with that equal sign in the discrete case. So then we just plug in values for that into the CDF function for a standard normal distribution, and we're done. Okay, so thus this probability can be approximated this way. So, but here's a note that people kind of mix up sometimes. The central limit theorem and convergence and distribution does not say anything about the asymptotic relationships of the PDF. And it's often the case that the PDFs do not converge to another PDF. We don't know that, but in some cases they do. So let's look at an example here. So let's look at a normal approximation to the binomial. And let's let n be 200 and p be a half. And we want to find this probability here. Now notice that there's an equal to sign, so we need that. We need to take that away. So we could say Sn is strictly greater than 94 instead of saying greater than or equal to 95, and that's what we have to do in this problem. So the mean of our data, it's a binomial, so it's NP, so it says that's 100. And the variance is NPQ, which that equals 50. So then we're trying to find this probability. Remember, I switched it to strictly greater than 94 because binomial takes on integer values. So then we subtract the mean divided by the standard deviation everywhere, and we get this. Then we can take the difference of the CDS of the normal distribution. So this value goes here, this value goes here, and we get 0.56222. So now, if we were to do this exactly, this would be the value. And look how close they are. That's pretty darn close. But, you know, back years ago, doing a binomial of 200, that would be unheard of, because 200 factorial, I don't even think a lot of calculators calculate that. But, you know, some do, some don't. So nowadays, that's not as big a deal, but it used to be. Now, there used to be, we can also do what's called a continuity correction. And so if we add the continuity correction in, we get this, which is even closer to the true value. But one note, why does the continuity correction work? Okay, well, the continuity correction works well because of the probability mass function, the binomial, ends up being very, very close to a normal distribution. So in this setting, it can be shown that the binomial converges to a normal distribution. Now, I didn't prove that. The video is running long anyway, but I think it's a fun proof. It's not a straightforward proof, and to do it by yourself would be, means you're pretty darn creative to be able to do that. The PDFs do converge in this case. So now here, this is the normal proxy to the Poisson. So the mean and the variance is lambda. So if we let lambda be 16, and we want to find this probability. Now notice there's no equal to sign, so it's in the setup in the format that we want. So we subtract the n lambda and the standard deviation was the square root of that. And so this is approximately, you plug in that value and plug it into the phi, and then this is -1, plug it in, and you get this. Well, that's all I have for today. Hopefully you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. In the next video, we're going to look at the law of the large numbers, specifically the strong law and the weak law. Now, the weak law is pretty cool because it doesn't assume that you have a finite variance, and it still converges in probability. And we're going to prove it two different ways, with the assumption of a finite variance and without the assumption of finite variance. And anyway, so that's it. I'll talk to you in the next video. Thanks. Bye.